So again, my name is Rex Hafenstine. Today I'm going to talk about a skin wearable wireless pH sensor. I am an undergraduate in the Biomedical Engineering Department here at Wichita State University. My mentor is Dr. Yongkuk Lee, and we work out of the BioIES lab. So wearable devices are gaining popularity in the general public right now. One of the big things you'll notice are smartwatches, heart rate monitors, and smart jewelry. How many actually individuals in here have a wearable device to monitor your behaviors? Few. One of the drawbacks with these is that they are bulky and they only record your behaviors. They do not work with finding out what's going on inside of your body, and so they don't allow accurate health monitoring. Thus, what we have devised is a skin wearable monitoring device, very similar to a tattoo. So in the picture you see there, go woo. It is going to be integrated onto the skin, low profile, it's flexible, and lightweight. It is also going to be comfortable for extended hours of use. One of the benefits of this is improved health monitoring. As I said, with the other wearable devices, they only work with behaviors. They do not record what's going on inside your body physiologically. There are different types of biofluids that you can find in your sweat, or different types of biofluids. There's sweat, tears, blood, urine. There's different ways that you can collect these. Invasively, if you are diabetic, you need to prick your finger. That is invasive. You are penetrating the skin. What we're looking to do is something that is non-invasive. You do not have to pierce the skin. It's something that you can gain data without having to pierce the skin. We are looking towards sweat because there are many different biomarkers in sweat. There is sodium, there is ammonia, glucose, many different things that you can gain from it. Currently, what we're working on is a pH sensor. Our goal is to concentrate on this one device so that we don't have a huge breadth that we're trying to work on, keep it very simple, and then work on it from there. Our prototype is a wearable sweat monitoring device that will be placed on the skin. So there are many different ways that you can record data. The reason why we chose a solid state sensor is it is easily able to be miniaturized, and it has ultra thin properties. The way that we work through this is through electrochemical deposition. We are taking iridium and we are placing it onto a platinum wire through electrochemical process. So there is an equation that we use to help us define whether or not our sensor was working properly, and that is the Nernst equation. So based off of the iridium, it has been found experimentally that at a negative 59 millivolts per pH is a good reading for the sensor that we're trying to develop. The sensor that we're working with is going to utilize a two-electrode system. There's going to be a working electrode and a reference electrode. So a little methodology behind it. We started off, well, I'll go through the working electrode first, which is the one that's actually receiving the information. The reference electrode is a base electrode so that you get the differences between the two. We started with the platinum wire. We went through a cleaning process. From that cleaning process, then we went through the electrode deposition, which you can see on the top right corner. That's our setup. Utilizing a power supply, we were able to deposit the iridium onto it. From there, after the iridium is deposited onto the wire, we coated it with a Nafion deposition to help keep that coating that we placed on there. Next, we went with the reference electrode. We started with the silver wire. We deposited iron 3 chloride onto it. Following that, we went with the 6-mercaptan-1 hexanol with the final deposition of Nafion. The process involved a total of 60 samples. So it's not like you just go out there and you try to develop something and all of a sudden, boom, it works, because that doesn't happen. Halfway through it, we started finding that we needed to dive into some other materials and find out what's going to work. So different conditions that we tested were cleaning, pre-treatment of the sensor. So we found in literature that we weren't getting the results that we were looking for, and they went and pre-treated the sample with the pH 7 buffer. We needed to check to see if we could shorten the amount of time that we were placing it in the 6-mercaptan-1 hexanol and the percentage of Nafion. The materials that we used were a test solution, which was a pH 4, pH 7, pH 10 buffer. And as you can see in the images, we had a computer, which was our data logger. We used a digital multimeter to be able to get the potential differences that we found in the solution. And then the bottom picture is a picture of a working electrode and a reference electrode and the test solution. So one of the biggest things that we were trying to find out is our sensor wasn't working properly. So we started looking at it microscopically. And we found that the iridium wasn't being coated onto the platinum wire uniformly. Finding that out, we learned that we needed to clean the wire, get rid of the impurities. It helps iridium adhere better to the wire. Also, I had spoke about the pretreatment of the pH 7 buffer. As you'll notice in the bottom diagram, the red line is what we found to work the best. So there is a cleaning and treatment process that we used, and it had a very quick response, and it stayed stable throughout the process. When we didn't clean it, it had a very big drift. When we cleaned it, but we didn't pre-treat it, it didn't respond as quickly as we wanted to, because when you put it in when you're using a sensor, you want it to respond as quickly as you can so that you get very good data. The 6-mercaptan 1-hexanol. We were trying to shorten the time of the manufacture process, because after you start going through 30 of these sensors and it's taking you a day to build 5 of these things, it's kind of time. You need to figure out how to speed this process up. So we tried to figure out if that was really a necessary step in the process. As you can see, the blue line, we tried it without the mercapto. The sensor fell off immediately. It didn't have stable results. The red line is 6 hours. So we cut the time from the literature. They were saying 24 hours. We cut it back to 6. We had a very good response. It was very stable. Therefore, we cut the time down. The percentage in Nafion, we tried many percentages in Nafion. Here I just show 2 different results. One of them in the red is a 1% Nafion coating. The one in the blue is a 5% Nafion coating. As you can see in the box on the left, very quick response time with the 1%, 5% as well, but the 5% has a very slow, after it gets in there, when you change the solution, it doesn't respond quickly. With the 1%, it did respond quickly. Before, when I was speaking of the Nernstian equation, the graph on the right-hand side, it shows the slopes of the 2 lines when you check them at the different pHs, the 4, 7, and 10. The pH, the 1%, follows, it is actually a super Nernstian. It's actually better than what they said in the information, so that's where we were able to determine that our sensor is working properly for what it's supposed to do. And discussion, after testing these different conditions, such as cleaning, pre-treating of the sample, the mercapto, how long we coated it for, we found our final sensor design. The reference electrode is a silver-based reference electrode. We're using a silver wire. We determined that cleaning wasn't necessary with the reference electrode. It worked just fine without it. We changed the time for the iron 3 chloride to 3 minutes from 1 minute in literature. 6 hours worked fine for the mercapto deposition, and we utilized a 1% Nafion. Similar on the bottom one, the working electrode, it is iridium oxide-based electrode. We used a platinum wire. We treated it with a cleaner and 1% Nafion, and we pre-treated it for 24 hours in a pH 7 buffer. The impact of this sensor, what we're looking at here, is its real-time monitoring. So when you were wearing your wearable device, it's giving you information for your behavior, but it's not giving it for your health. So what we're looking for right here is we're going to get real data from your body immediately. Hoping that this is going to create a reduction in healthcare costs, because it's going to alert you earlier about what's going on with inside of your system before you find out, hey, I need to go to the doctor, and it's too late. So hopefully help reduce healthcare. Improved healthcare awareness. If you know what's going on physiologically in your body, it possibly could have an impact. Of course, you can tell me a lot of things to do, and I might want to do them or not, but the goal is it's going to have a help. Future work. We want to be able to have this sensor communicate wirelessly. We all have our phones with us, so near-field communication so that you can get the data right off of your device. Like I said in the beginning, we are working right now primarily with the pH sensor, but we want to incorporate other sensors in there as well. Glucose, we want to measure sodium, we also want to measure the sweat rate. All of these things have an effect on how your body is working. We want to test them on human subjects as well, which means we're going to have to go through the IRB. These are my references. I want to acknowledge McNair's program staff. I visit them constantly, and without their continued support, helping me get through this, there's a lot of work that goes into this, and you need a support group around you to continue to push you forward, because it's necessary. That's all I'm going to say. And my mentor, Dr. Lee, he keeps me on track. If it wasn't for him, we have discussions very often, and I need his support as well. Dr. Lee would like to acknowledge a startup fund that he has received from Wichita State University. And I want to thank you all for listening. If you have any questions.
Excellent and quite interesting. So let me make sure I understand. So you would put this at some place on the body?
Yes.
And how long would it last?
The goal is to have it last where it's going to be able to stay on there for the day. It could even stay on there longer. It all depends on what kind of data that you're looking to gain from it. So it's not going to be a short-term device. It's going to be something, so the response, the reason why response is important is because during the day, your body has changes in what's going on, right? So you want to be able to record, okay, something's happening in the morning, something's happening here, why am I getting tired in the middle of the afternoon? What is going on? And these correlations between your blood and your sweat can help you to determine, okay, what physiological changes are going on so that you'll be able to wear it through the day. It's going to be variance because it's going to be small. We're looking at it right now for the amount of the array size that we're working with. It's about 1/4 in size. Of course, the more things that we add on there, it's going to increase the size, but we're hoping to keep it about 1/2 inch to 1 inch in overall area. And it's going to be something that you can place wherever. So in the image that I showed you, so there's 2 different types of sweat glands. One of them is your eccrine sweat gland, and your other one's your apocrine. So one of them it's going to have your sodium and different things like that. Your apocrine, which goes through your hair follicle, that's more of your hormones and different things like that. So it's going to be on the scan, but there's going to be certain places where you would want to mount it and other places you wouldn't. You want to put it underneath of your underarm because that's not going to give you the kind of data that you're going to be looking for.
So you would use on adults and children, or at this point just on adults?
For both, to test, because one of the things with sweat is that you can, there's different diseases and stuff that you can find out early for younger individuals to maybe help them. That way they don't go down this track and have to be medicated for the rest of their life. Sweat's used a lot for cystic fibrosis, so